There we go. Okay, so now it's my pleasure to introduce Dr. Neil Hutchinson. Dr. Neil Hutchinson became passionate about environmental science as a teenager and coupled its emergence as a discipline with his personal attraction to water and Canadian geography. He completed an honors Bachelor of Science in Ecology at the University of Guelph in 1978 and his PhD in zoology at Guelph in 1985. He then came to Muskoka to work at the Dorset Environmental Science Centre, which is a portion of the Ontario Ministry of Environment, in 1984. Having worked on water quality from Newfoundland to BC, from Southern Ontario all the way to Nunavut, he considers himself fortunate to have taken part in the great strides made in environmental management over his 47-year and counting career as a summer student, as a graduate student, government scientist, consulting scientist. He grew and managed his own consulting firm, and then finally in his retirement in 2022 into his current role as a hobby scientist. His major career highlight was being introduced as the Mick Jagger of lake management several years back, which sounds like quite the honor to me. He was a founding member and served on the board of the Muskoka Heritage Foundation, which is one of the parent organizations of the Conservancy. And he now sits on the board and committees of several environmental organizations in Muskoka, including the Muskoka Watershed Council. He's the chair of the Science Committee for Georgian Bay Forever, and he's also on the board of Friends of the Muskoka Watershed. And he's also a member of the Rotary Club of Bracebridge since 2016. He now lives on the shore of a small lake outside of Bracebridge in a home which he shares with his wife, Barb. Their 3 daughters all have left Muskoka, and he also has 2 happy dogs and 2 mini black flies that he has to share his space with in June as well. So thank you, Neil, so much for joining us today. You now have the floor. Your slides look great. And yeah, take it away.
Thank you very much, Amanda. Can everyone hear me okay?
Yes, you sound great.
Great. I'm going to start this with just a few personal reflections. And as Amanda said, I've been at it for a while and watching things. Here's the observations I've made. They may not be complete, but they are the things that have stuck out for myself. And just a bit of personal history, just some sorted slides here with Mick Jagger in the center, of course. But up in the upper left in the middle was 2 entertaining years as a summer student pumping air into the bottom of Hamilton Harbor to try to turn it over. It was at that time one of the most degraded water bodies in Canada. And we put 4 2,000-foot lines into the harbor and tried to turn it over to try to get oxygen down to the bottom, which was quite an interesting process. Graduating from the University of Guelph, meeting up with colleagues and friends at conferences, sampling sewage in Alberta, and presenting to the Senate of Canada with some Inuit colleagues back about 4 years ago. So just some interesting things that have happened along the way. But my own personal milestones I've kind of divided them into water quality eras in Ontario and what the concerns were at the time. When I was in high school, DDT had been banned. It was immediately post-Silent Spring. The emergence of the environment as an important concern. Lake Erie was dying. Phosphorus was too high in the Great Lakes. And this was the thing on everybody's mind was dead fish in Lake Erie. And public awareness really became a thing. When I was at my undergrad in Guelph, we saw the beginning recovery of the Great Lakes with point source nutrient controls, the Great Lakes Water Quality Agreement, to getting phosphorus out of detergents. And we learned how to manage by tackling the point sources, the big pipes that were putting pollutants into water bodies, and found that if we controlled the pollution from that point, the water body would recover. Staying at Guelph for my PhD after working for a year and a half, the early 80s were the time of the emergence of organic contaminants as a concern. Dioxins and PCBs and furans and Love Canal were poor disposal practices that contaminated the whole neighborhoods. I was working on an acid rain related project, and acid rain was the first time we had to look beyond our own borders to manage the pollution that we were suffering in Muskoka. Our sulfur dioxide pollution was coming not only from Southern Ontario, but from the Ohio Valley and the industrialized parts of the United States. We started working on watershed management in the 80s, moving away from the big pipe to look at land use practices, agricultural and urban runoff, lakeshore capacity, cottaging impacts to water quality. And again, expanding our view away from point sources and big pipes to continental management and watershed. I came up to Dorset worked there for 14 years. And during that time, Brian Mulroney, the late Brian Mulroney, negotiated the Montreal Ozone Protocol to take care of the ozone hole, engineered an acid rain treaty with the USA that cut our acid rain emissions drastically. We saw successes in continental management our pollutants all over the continent with success, and over the planet for the Montreal ozone. So we had point source and source controls, phase outs and bans. We were just saying some contaminants we're not going to use anymore, and getting rid of the worst of the worst. We then saw invading species, biological pollution. Zebra mussels became the big issue in the late 80s and are, of course, still around. The zebra and quagga mussels have just made the Great Lakes their home. We don't have enough calcium in Muskoka to support them, so we've been lucky. But we have things like the spiny water flea, species that once they're here, you really can't get rid of. And then working in the private sector for the last 23 years, saw the emergence of advanced sewage treatment technologies, where you could treat sewage almost to the point of drinking water quality. We saw the emergence of pollutant trading and whole watershed management, the emergence of multiple stressors, how to figure out what's going on in our water bodies when several stressors are acting at once: acid rain, low calcium, chloride from road salt, which we'll talk about later, and of course, climate change became the big issue that's still with us. Over that time, I saw a recurring theme in environmental management, and you can apply this to just about any environmental concern. Scientists would observe some form of environmental degradation. The public would get concerned and start asking questions about it. Scientists would go in and try to figure out what was going on and demonstrate what was causing it. The first response would then be denial and pressure from polluters, and often from politicians too, is that this is a natural factor, or there's nothing we can do about it, or if we were to tackle this, we'd lose an industry and have economic mayhem. We still hear this form of denial in climate change. The scientists generally persisted, though. Public pressure was maintained, and in the end, political will brought about management and solution to the problem. And regardless of the problem, this is kind of the successful path that we've seen with the bumps and valleys along the way. So let's talk about phosphorus in the Great Lakes and how that aligns with my steps of degradation and management. Well, we saw algal blooms, cadophora, and loss of oxygen, anoxia, in the bottom waters of Lake Erie in the 60s and 70s. Now, I actually had a Maclean's magazine that pronounced Lake Erie dead. And at one point, they suggested putting a dam at Detroit and reducing Lake Erie just to a river and exposing all that valuable farmland that was highly nourished, of course. And of course, that was just a pipe dream and it didn't happen. But that was the type of thinking people were thinking about. Scientists said the phosphorus is the problem here. It's the limiting nutrient. We're putting too much phosphorus into Lake Erie. That's why we're getting all the algae and the loss of oxygen. The industry said, no, it's not. It's carbon, it's nitrogen, it's all these other substances that we're putting in, and not phosphorus. So leave the phosphorus alone. Dr. David Schindler did the definitive experiment, which you can see on the picture on the right. There is a membrane stretched between two halves of a lake in northwestern Ontario. The top side, the clear water, has carbon and nitrogen added to it. The bottom side, the green side, has carbon and nitrogen and phosphorus added to it. This made the cover of the world's most respected scientific journal and resulted in a lot of public pressure, political will, ending up with the Great Lakes Water Quality Agreement, phosphorus limits in detergents, and phosphorus removal at our wastewater treatment plants, to the point where Dr. Noel Burns, a scientist with Environment Canada, published a book called Erie, the Lake That Survived. And up until recently, Lake Erie was doing quite well. Now we're seeing some nasty algal blooms emerging there again. But in this case, the phosphorus story followed the pattern. And just here's an example of wastewater treatment plants and all of the municipalities in the Lake Erie watershed with the numbers here are the phosphorus limit in the sewage of 1 milligram per liter or half a milligram per liter or 1.5 milligrams per liter, depending on the size of the municipality. All the big municipalities are down to 0.5 milligrams per liter, which represents about a 95% removal of phosphorus from the sewage effluent. So very important, you can see the number of sewage plants in the watershed and the importance of managing these types of effluents. And managing them we did. Raw sewage with no phosphorus removal contains anywhere from 5 to 10, usually averages about 8 parts per million. The Great Lakes Water Quality Agreement got that down to 1 milligram per liter as a requirement. By 1985, new plants were asking for 0.5, and you could see that the limits in the sewage plants kept dropping and dropping. Just for a reminder, our Bracebridge plant has a limit of 0.4 milligrams per liter. The new Huntsville Golden Pheasant plant has a limit of 0.3. Now, those are the legislated limits. We expand the scale on the left, the phosphorus. We'll see that in 2005, 0.1 milligrams per liter. Huntsville actually achieves 0.05 milligrams per liter in their effluent, much better than they're required to, and Bracebridge 0.04. So these are superb, well-polished effluents that we're seeing here. One of the last projects I worked on as a consultant was a new sewage plant for Upper York, which was going to have a limit of 0.02 milligrams per liter. I gather Doug Ford has since canceled that project. But we built a plant with 0.07 milligrams per liter in 2010 at Alcona on Lake Simcoe. These red lines show the Ministry of the Environment's water quality objectives for streams of 0.03, for high nutrient lakes of 0.02, and for Muskoka lakes of about 0.01. You can see that we're capable of treating sewage phosphorus to the point where the sewage itself would meet the water quality objective. We've done a very good job on that. And of course, the Great Lakes responded. All of the Great Lakes, especially Lake Erie and Lake Ontario, have dropped down substantially since the 60s in their phosphorus concentrations. So we solved the effluent phosphorus problem. We've solved many other end of the pipe problems. Here I am sitting on a sewage outfall in central Ontario, and it wasn't the end of the world, and it wasn't the end of profits. Here's Canada's gross domestic product. It keeps continually increasing over all this period since 1969, when we put in all these industry-killing environmental policies in place over this period of time. Well, let's look at acid rain now. Here's again my theme on the left here of the steps that we go through, and we'll just follow that with acid rain. Our colleagues at Ministry of the Environment had been working in Sudbury studying extreme acid rain from the smelter effects up there, and they finished that study and they moved to Dorset to start studying phosphorus in our Muskoka lakes and lakeshore capacity issues, and they found that the rain was still quite acidic. Even when the Sudbury smelters went on strike for 17 months, we found that we're still getting quite acidic rain here. So lots of science across Canada looking at the sources, the fates, the linkages, and the effects, and saying that the problem was sulfur dioxide. Industry people denied it, obfuscated, said it was natural, said it'd kill the industry if we were to deal with acid rain. Dr. David Schindler did another persistent definitive experiment where he acidified a lake, again in the experimental lakes area in northwestern Ontario, and dropped the pH down to abnormal levels. And the lake trout, which started out fat and healthy, became very, very skinny. We killed off their food base. The fathead minnow was a big important one there, but several other fish, and they basically starved to the point and stopped reproducing. When the acid was cut off, the fish came back again. So again, they simulated the effects of acid rain, showed quite conclusively that sulfuric acid was responsible. Public pressure was applied. Political will was applied. Our own MP, Honorable Stan Darling, took the case to Ottawa, worked with Brian Mulroney, and ended up with a Canada-US acid rain treaty that effectively managed acid rain. So we can see over this period of time, huge drops in emissions in the United States, substantial drops in emissions in Canada, and of course, our gross domestic product still keeps increasing. So it wasn't the end of the world, and it wasn't the end of profits. We still end up with profits. And here's all of the different approaches to environmental management. We've seen here Canada's gross domestic product here, whether we're banning toxics, whether we're controlling effluents with big pipes, whether we're managing the watershed or the airshed, we are still seeing our gross domestic product ticking along pretty fine. But wait, we do have problems in our gross domestic product. Well, in 2008, the bankers' savings and loan scandal in the States, the bankers crashed our economy. In 2015, the price of oil crashed. And again, 3 years ago, COVID came in. So here are our big social phenomena that seem to decrease our gross domestic product, but we don't see that response to environmental controls. So my lesson here, my message here is let's just get on and do it. But now we go to our climate change story. I learned about the greenhouse effect in my 1974 ecology textbook. Scientists were raising concerns in the 1990s. We had denial and life as usual. We had the Rio Summit in 1992, the Kyoto Summit in 1997. Life went on as usual. Scientific persistence. We've had every 5 years a report from the Intergovernmental Panel on Climate Change, none of which seem to have had a lasting impact because we're still carrying on as life as usual. Doug Ford's government is actually increasing acid rain or carbon dioxide emissions over the course of their term. We've had the emergence of climate change deniers, both in the public and in the political sphere, no political will, and ineffective actions. So we're stuck here with climate change, and we're not quite sure what to do about it. And I'll provide some hypotheses about that. But we'll see that atmospheric carbon dioxide certainly is rising with global, there's our global emissions. There's about the 1950s era when it started, late 50s, our emissions skyrocket. And of course, our atmospheric carbon dioxide over the same time period, that arrow starts at about 1959 as well. And we see emissions going up, atmospheric CO2, and the resultant effects that we've seen. So that's 3 case studies. What I kind of see, what I'm going to call good news in our trends over the course of my career is we've gone from managing highly toxic things that are toxic in the parts per billion and parts per trillion, like DDT, PCB, dioxins. And over time, the toxicity of what we've managed really is lower than it used to be. Then we got to ammonia, metals, and mercury. We're getting into things like total suspended solids, which is just plain dirt, clay particles in the water, bacteria, phosphorus, naturally occurring substances, sulfur dioxide, which isn't particularly toxic, calcium and chloride, and carbon dioxide. Many of these things are essential for life, but we're stimulating secondary ecological effects and not the direct toxicity that we used to see. A whole different way of dealing with pollutants. They're less toxic than they used to be, but they're stimulating these secondary effects that we need to start considering. The bad news, of course, is that over the same period of time with the same pollutants, they're coming from more sources. It was quite easy in retrospect to tell the big chemical companies to quit making DDT. It was easier but expensive to regulate the big pipes, the effluents, and say, sorry, you guys are going to have to start treating your pollutants and getting the effluent levels down. And then we had to move into things that were a bit more complex, managing municipalities and individuals and industry within a watershed for some of these less toxic pollutants, moving into continental management, all of North America to deal with acid rain, and now working through the whole planet to get our carbon dioxide emissions down. So while the pollutants are less toxic, they're coming from more sources, which adds more complexity to what we have to do. So the evolving management, we banned the worst, we control the big pipes, we manage the watersheds and the airsheds, and we have to manage the planet. And you'll see that the responsibility for these have moved from the corporations down to the businesses and the municipalities and landowners when you're talking about watershed management, airshed, intergovernmental, other governments, other countries, other governments, other countries, and individuals to manage the planet. What we're learning with climate change is we can't just point the fingers at big industry to the extent that we used to. In the matter of fact, we have to start managing how we choose to live. So all these require government leadership, pressure on the various actors to achieve the end. But government leadership only comes about through public pressure. And that's where our responsibility is to pressure our government into taking the right actions. And so the evolving responsibility we've seen is, in the end, the polluter paid through their profits, lessened profits or higher prices to manage the pollution. And for corporations and businesses, when we get down into the watershed level, municipalities and landowners, our taxes are more often going to fight pollution, whether it's to keep our sewage plants operating or to work on some of our urban land use issues, and better planning policies all take a bit of money. And ultimately, the polluter can pay with changed behavior as individuals. What we come to expect from the land and our own desire about what we choose to put on the land will influence the outcome and the quality of our water. So, as this famous cartoon shows, we can manage the planet, and we manage it through individuals. We have met the enemy, and he is us. We are the problem. We are the ones who influence what's happening in the planet around us. And as Chris Hadfield, our astronaut, says, we have a problem. And his book I found was quite fascinating as a guide to managing water quality, because he said anticipating problems and figuring out how to solve them is not the same as worrying. It's productive. You can imagine as an astronaut and how tenuous your hold on survival is when you're living in space. You have to anticipate everything that can go wrong and find a way to deal with it. And he says it's not the same as worrying, it's productive. Coming up with a plan of action isn't a waste of time if it gives you peace of mind. So we have to recognize and come up with actions and get the peace of mind that our planet will sustain us. He says, well, it's true that you may wind up being ready for something that never happens. If the stakes are at all high, it's worth it. And we see that. Well, what if climate change isn't as bad as we think it is? Whether if we just get shorter winters or something, what we may get in the process of doing that is cleaner air and better equity. And this is another famous cartoon here is what happens if climate change is a big hoax and we create a better world for nothing with energy independence. We don't have to rip the ground apart to get oil out. Preserving our rainforests, having a sustainable living, livable cities, renewables, all these good things that you can get with better environmental management, which are kind of no regrets actions. So we're going to move from there, and we'll talk about some very more focused work on road salt and what we've been working on there with Friends of Muskoka Watershed in Muskoka, and working with my colleague, Dr. Norman Yan, on road salt, which again is a great example of everything from our own personal responsibility to pressure on governments to take action as well. A lot of the work we're doing has got a lot of partners: the Dorset Environmental Science Center from the Ministry of Environment, Queen's University Research, York University Research, District of Muskoka Water Quality Sampling, and the Gull and Silver Lakes Residents Association in Gravenhurst, who've been very, very helpful. So talk about road salt. It's really the same formula as our table salt. It's just not as clean as our table salt, but it is sodium and chloride bound together. It's an essential element. We need bits of both, but too much salt is harmful. Just ask your doctor, he'll tell you that. But we apply it to roads, parking lots, driveways, sidewalks to melt ice and snow so that we can move safely and quickly about in the wintertime. Chloride is the most toxic component of road salt, and we'll talk about that. That's going to be the focus. And it's very interesting is that it does not degrade naturally. Once it's in the system, the only way you can get rid of it is to dilute it with fresh water or by turning off the source. It doesn't tend to fall out of solution and get buried in the sediments. It doesn't degrade into different substances. Once it's there, it's there. Road salt is the source of chloride in our waters in Muskoka. This graph here shows chloride across the side and sodium across the bottom, and a very strong relationship between the two, showing that when there's chloride, it's there because of sodium. We also do, in some of our catchments, we add calcium chloride to our roads for dust suppression, and you'll see that the relationship there is much looser. We can't always say that you can predict how much chloride is there on the basis of how much calcium is there. You can with sodium. If we look at, again, the benefits of long-term monitoring, these are our Ministry of Environment data from look at the Big East River upstream of Huntsville. The only real land use is Algonquin Park up there, a bit of logging, a little bit of cottaging. But since 1983, so over the last 40 years, we have seen 60% on average reductions in many pollutants coming into the Muskoka River system. Chloride is down from road salt chloride is down, probably because atmospheric dust is down. Copper, ammonia, phosphorus, sulfate, all of these have decreased. If we go down to the bottom end of the watershed in Bala, you'll see the same pattern that all of these pollutants have decreased by about the same amount, except for chloride, which has increased by 90% in the Muskoka River at Bala in the last 40 years, compared to decreasing at the top of the watershed. Once you go through Huntsville, Bracebridge, Gravenhurst, all our smaller municipalities, we have added chloride, substantial increases, and it's measurable where the river flows out at Bala. It's happened in Muskoka Bay and Lake Muskoka. The blue dots here are showing right back to 1970, 1969, which are pretty much baseline levels for chloride of about 0.5 part per million, a slow, steady increase in Lake Muskoka over that time period, and even more severe increase in Muskoka Bay, Gravenhurst Bay, which is, again, surrounded by urban development in the town of Gravenhurst, and is also cut off from mixing with the main body of the lake by the very narrow channel that's been blasted and opened to go from Muskoka Bay into Lake Muskoka. So, and these increases are still happening. With the Watershed Council, Muskoka Watershed Council, I analyzed the District of Muskoka's data, and I can't emphasize how important it is that the district get out to our 270 lakes every 2 years. Every lake gets sampled in the springtime to keep a long-term idea of what our water quality is doing. So you'll see that only about 35% of our lakes are less than 1 part per million of chloride, which could be considered pretty much baseline, what it should be. So 70% of our lakes have increasing levels of chloride until we get levels as high as 60 to 120 parts per million, substantial increases in over 40%, 30% of our lakes are up into quite interestingly high levels. The bottom graph shows how much they've increased in the last 5 years compared to the last 15 years. So we'll see that here, the biggest bar here is that, again, 75% or so have increased or decreased or less than 0.5 part per million. Not enough to really set a trend because it could just be statistical and sampling noise. But the higher you go, we'll see that we have lakes that are increasing by 1, 2, 5, 10, even more than 10 parts per million over 5 years over their period of record. So that shows that the problem is ongoing and our lakes are increasing in chloride. So where does that come from? Well, we use 5 to 7 million tons of road salt per year in Canada. 2.2 million tons of that are in Ontario, which corresponds to about 200 of these Great Lakes freighters. We use 60,000 tons per year in Muskoka, which corresponds to about 1 ton for every permanent resident, which is equivalent to 4 of these pallets that you might see at the hardware store. And that's not saying that we as individuals use that. That means that the cumulative total of road salt that's applied to our highways, our municipal highways, our parking lots, our own sidewalks, those type of things add up to 60,000 tons per year. And how does it get into the environment? Well, we can store it and keep it safe under these big domes, but you also see there's quite a bit of spillage there. That's not going to help anybody stay safe on the sidewalk. That's just going to run off. We apply it inaccurately and too much to our highways, and it just bounces off to the side where, again, it doesn't help anybody, but it does run onto the drains and down into the water body. We get aerosols of salt from the traffic going by, and we get the bleaching of our pine trees along the side of the roads, which are suffering from road salt. And of course, we just have over application, adding way too much because we figure if 1 ton is good, then 2 tons have to be twice as good. And often 1/4 ton would be just as good. So we do tend to over apply it, and we apply a lot of it. So why is this a problem? Why is this increase a problem? Well, we'll talk about toxicity here first. This is, again, Gravenhurst Bay data, Lake Muskoka data. Well, chloride is toxic to sensitive aquatic life, and we're going to spend a bit of time talking about invertebrates. Here are water fleas, almost the base of the food chain. Norm Yan has spent his whole career looking at these creatures. They are just barely visible to the naked eye, and there are trillions of them in Lake Muskoka. Daphnia or bosmina, two key species. Quite interesting little animals. Really critical food source for fish, for young of the year fish. Just chow down on these. Very important. Well, the federal government recognizes that chloride is toxic, and they set a guideline through a scientifically valid process that said if you have 120 parts per million or less, that should be fine for the long term. That was using data from all over the world. So it says that most life is protected below 120, but what we've learned is chloride is much more toxic in our Muskoka waters, which are very low in calcium. Our waters are low in calcium for two reasons. One is that we're on the Canadian Shield, which is very resistant to weathering and doesn't have a lot of calcium compared to the limestone, the geology of Southern Ontario. And also over 30, 40 years of acid rain, the rain leached a lot of the calcium out of our soils and down into the waters and downstream, and it's now in the Atlantic Ocean. So chloride is much more toxic in low calcium waters. So here are 6 species of Daphnia, and then Daphnia mendotae there, which show that once you get it to about 120 milligrams per liter, you really suffer. You're really hitting the reproduction. This is reproduction as chloride increases, the number of babies decreases. With the Daphnia galeata, Daphnia mendotae, by the time you get up to 30, 40 parts per million, you don't have any reproduction, really. At 120 milligrams per liter, you've got pretty much 100% reproductive failure. And these are lab studies. These are done in the lab at low calcium. So what we know is that the 120 milligrams per liter is not protective. And we do have that in lots of our lakes. So there's a Canadian Water Quality Guideline of 120. One of Norm Yan's students found that Daphnia was impaired at 40 milligrams per liter. And Dr. Arnott from Queen's University found that at 10 milligrams per liter, reproduction was very severely impaired. So that means that 120 is not protective. 50% of our lakes fall within this range. So 50% of our lakes are less than 10 milligrams per liter. 75% of our lakes are less than about 25. And we have lots of lakes going right up to 120 parts per million. So we have many lakes in Muskoka. 25% of our lakes are sensitive to chloride toxicity by virtue of their low calcium concentration. So we do have a problem. Not that the federal guideline was done improperly, it was done in a valid state of mind, but it did not include enough studies done in low calcium water that we have here. So we need to revisit that. And we also have Jevons Lake is down at the south end of Gravenhurst. And here is it from 2004 to 2024, increasing from about 75 parts per million to 110. Periods of low salt or high runoff had low values there in 10 years ago, but it's steadily increasing. Now, Jevons Lake is situated right where the big bend in Highway 11, when you're coming north up into Muskoka, it's down to the right, and it receives not only the Highway 11 drainage, but all the drainage from the south end of Gravenhurst, where the grocery stores are and the Home Depot and all those flowing into a wetland by the McDonald's and then out, down, and into Jevons Lake. So we know it's increasing over the last 20 years. But 20 years isn't really that far. How far back can we go? Well, this is a complicated science called paleolimnology, and it uses the remains of animals that are preserved in the sediments, whether they're algae remains or zooplankton remains. They get buried in the sediments. And you can go out and take very thin layers of sediments and date them using basically isotope values to find out how old they are, and then you can reconstruct the assemblage of aquatic life that was present there. So if we go back to about 1950, we'll see that prior to that, going back hundreds of years before that, really no change over time. But over the last 70 years, we see a steady downward trend in bosmina in one of these Daphnia species, which is sensitive to chloride. Then we see increase in other species which are tolerant of chloride. So we know by digging back into the past that the animal life in Jevons Lake has been changed by road salt, and that the lab studies show that it's toxic. So that's an important factor to consider, is that increasing chloride toxicity is damaging to our aquatic life. I'd like to talk a little bit about mixing of lakes and how important that is to the lakes that we see in the spring and fall. In another couple of weeks, all the ice will be gone off the lakes. Given this spring, it may happen next week, who knows? But water is most dense at 4 degrees. And right now, in the bottom of our lakes, we have a cold bottom layer of cold water of 4 degrees or less sitting at the bottom of the lake with an ice layer protecting it. When the lake warms up and the top water hits 4 degrees, it's the same temperature as the bottom water, the wind will mix the whole lake from top to bottom. And that's very important because it's moving oxygen from the surface water down into the bottom waters where sensitive aquatic life needs it. So that is very, very important that that mixing occur. And it's very much driven by the density and is driven by temperature. As the summer warms up, the sunlight penetrates to about 8 meters in our lakes and warms up the upper 8 or 10 meters. And that gets warmer than 4 degrees, so it floats on top of the thick, dense water at the bottom and doesn't mix with it. And that stratification sets up late May, early June, and lasts till November, when it cools again, hits 4 degrees, and the wind mixes it again. So you can appreciate that all the oxygen that's locked in during the spring overturn is not going to see the atmosphere again till the fall, and is all that we have for the aquatic life to live by. So this mixing is very important in the life of our lakes. Now, the graph here shows that with water, when you add salinity to water, the density increases as well. So temperature not only changes density, but as you add salt, the density increases. So this can alter the mixing. So if density increases and the cold water, salty water sinks and resists mixing, because the salt comes in the wintertime and the water's cold, it'll sink and resist mixing, it's going to get harder even when the temperature hits 4 degrees, there's still going to be the salt density at the bottom of the lake. It's going to make it hard for it to mix. So we're worried that salt input can delay change and prevent lake mixing. And there's evidence of this happening in other lakes in Ontario. So this would reduce our near bottom oxygen levels. It would change the chemistry of phosphorus so that it might be released from the sediments if they lose their oxygen. It changes the habitat values of available fish, and it changes the life in the lake sediments themselves. So it's important that our lakes keep mixing on the schedule they have for all the aquatic life that's there. So last year, about this time, I went out with Spencer McPherson from Friends of Muskoka Watershed, and we measured a profile of conductivity, which is a surrogate measure of chloride in Muskoka Bay, and found that, yes, indeed, it increased with depth as the water was denser and had quite a substantial increase at the bottom. So we do have to be aware of this in some of our water bodies, that we may be changing the chemistry enough that the mixing may be altered. I'd like to talk a bit about what's going to happen as our climate changes. We think that there'll be more salt being added to the watershed because as the lakes stay open longer and we get enough cold wind coming in down over Lake Huron and Georgian Bay, that brings lake effect snow to Muskoka, and we certainly see it down at the south shore of Lake Erie, where the winds coming down from the Great Lakes bring lake effect snow. So if once Georgian Bay freezes over in a good cold winter, not like this winter, we tend to get much less snow. Usually our snowstorms are pretty much gone by the end of February. Most of our snow falls in December and January in a typical year. But with climate change, we're not sure that's going to happen. We're going to get more lake effect snow and more desire to add salt to our roads to get rid of, to melt it down. The other thing that forms ice on our roads is when you get a warm day, you get snow melt. And when the temperature drops overnight, it turns to ice and you get a slippery surface. So here's our data from our Muskoka weather stations, and this is the average daily temperature from December 1st, 2021 to March 30th, 2022, and we'll see that the temperature goes up and down. We get long periods where it remained below freezing, but we've got 6 episodes where the temperature dropped from above zero to below zero, which would create ice on the road. And that's when people would want to get out and salt it. Our climate models project that we're going to increase our average temperature by about 3 degrees by 2050. And of course, that's not that we'll still have variable average temperatures, but they're going to be varying about a higher mean value that's 3 degrees warming. So that means that instead of 6 of such episodes, these shoulder seasons here are going to become the episodes of, we end up with 10 episodes where we could predict more ice on the roads and more need for salt. So that's another reason to be concerned about our changing climate. So road salt doesn't stay put. It migrates into our waters and increases the chloride levels. And once it's there, it's there. Chloride levels are increasing in many of Muskoka's lakes. It can alter lake mixing with negative consequences. The federal guideline does not protect our typical Muskoka lakes, which are low in calcium. Our water fleas are damaged at about 10 milligrams per liter of chloride in the lab, and 20% of our recreational lakes exceed this. Chloride levels may well rise if we keep adding it as we get more development and the climate changes. And we think we have a widespread environmental problem to address. The problem is it's toxic and we keep using more of it. In 1999, the federal government declared that road salts should be considered toxic under the Canadian Environmental Protection Act because of tangible threats of serious or irreversible environmental damage. And yet we continue to use more than 5 million tons per year, and lots in Muskoka. So it's toxic, but we keep using more of it. Now, how necessary is this? And where are the problems? It's not just highway maintenance. There are lots of other sources here. Here is the back of a grocery store in Bracebridge, where here's the road salt and sand mixture that the contractor uses to spread all over the parking lot. And of course, he's just throwing a tarp over it. None of this is protected from rains. That's all going to get out, and it's not going to help the parking lot. It's just going to run off and down into the Beaver Creek drainage and down into Muskoka River. We tend to put too much on in different places here. That's way more than we need. Here's the Bracebridge LCBO and lots of excess road salt there and there, and where it's just been worn free by people passing there. There's an entrance into a municipal office in Gravenhurst. We spread it everywhere just because it's cheap and there's lots of it. The damage is not limited to a sensitive aquatic life. It damages our lakes and streams. It damages our drinking water, our soil, our trees, our infrastructure. The University of Western Ontario have just started a project to look at salt effects on steel. We see crumbling concrete from road salt and the need to replace our overpasses. We know what it does to our vehicles. It makes our vehicles more expensive because we have to rust-proof them and they wear out faster. It's hard on our clothing, it's hard on the paws of our dogs, and it's hard on our buildings. So salt damages are substantial. Canada's Eco-Fiscal Commission, which is a collection of economists and academics, estimate that the economic and environmental damages of road salt are about $680 to $3,900 per ton per year. So that works out to $41 to $234 million of damage per year in Muskoka from road salt. So there's environmental reasons as well as economic reasons why we should be reducing its use. Well, where's it coming from and how serious is it? Well, this is the role of citizen scientists, which we've been engaging. There's Clark Smith and Sandy Cairns, Gravenhurst councillor, who are all set to measure salt runoff down in Gravenhurst. And we've given them these little pens, which are about 6-8 inches long, and they measure conductivity, which is a surrogate for road salt, easily transferable surrogate. And then they can look around in their own neighborhood and measure runoff with more people looking at greater areas and more frequent measurements than say I could getting up and going down to my car every day. And we know this because here's conductivity across the bottom, and then this is a lab relationship with district data chloride there. Again, a very tight relationship between the conductivity that you measure with one of these and the chloride that you can infer from that. So measuring it directly is costly, but you can do it quite inexpensively as a surrogate. And here's what we found. Some of our citizen scientists have found. We drive up north towards Huntsville. Spider Creek crosses Highway 11 upstream. It's got a value of 22 conductivity units. Immediately downstream, it's nearly double to 36. Just one road crossing, one stream. Here's 8 or 9 different areas in Bracebridge and Gravenhurst, where the North Muskoka River is impaired, is altered. It's about 61 units, but you see commercial plaza drainage of up to 15,000 conductivity units. This is the commercial plaza where we saw the pile of road salt under the blue tarp. And residential areas, depending on their age and their size and how much salt is used, have enriched values. Commercial drainage areas also have high values and versus residential areas. So where we put more parking lots and more traffic, we get more conductivity. So we can recognize the problem, but what can we do about it? Well, with our friends at Gull and Silver Lakes and the Friends of Muskoka Watershed, and I'd add the Provost Club of Gravenhurst, encouraged the Gravenhurst Council, and last July they passed a resolution that whereas road salt has been declared to be toxic, the town of Gravenhurst commits to the reduction of the use of road salt as much as possible while maintaining safety on roads and sidewalks. Now, that's a good recognition that there's a problem and a recognition that we should start to do something about it. The big caveat, of course, is maintaining safety. How much do you need to do that? Well, what can we do? We can quantify our road salt and reduce it where possible. Improve our winter weather forecasting. We tend to think the weather's out, we just go out and sock the salt to the road. There are only certain weather conditions that bring on icing conditions, and we have to get a better handle on those. We could use less salt. We could use different formulations of salt, mix it with sand, apply it as a brine instead of big nuggets that drop off the road. One of the interesting things that's happened in the United States is in New Hampshire, where commercial operators, the contractors that spread salt over the parking lots on supermarkets and such, are very worried about lawsuits, about getting sued because somebody slipped on the ice and hurt themselves or had a car accident. Their insurance rates are skyrocketing because of this. Well, New Hampshire has said, well, we're going to train you and certify you in how much you really need to have to apply, and which is always less than what you do. And if you are certified and you have followed the requirements of that certification, your liability is limited, and people can't put you out of business if you follow the proper rules. So that's a very important step that could be taken to try to remove the liability and still maintain safety. Reducing its overuse. There will probably always be a need for some use, but it's the overuse that we really need to tackle first. We can have more winter tires on our car, make our car adapt to winter instead of the highway. Wear proper winter footwear, winter footwear that's better able to walk on ice. Slow down. We don't need to go 120 kilometers an hour year round. We don't need to do it most of the time anyways. Shovel more instead of throwing salt to do our work for us. Sweep up and reuse excess salt. Switch to sand and spread the word. How much salt do you need? If you have a 20-foot standard driveway or 10 squares of sidewalk, each of which is about a square meter, about 1 cup, a 12-ounce cup, is all the salt that you need to make that area safe. And yet we tend to throw on large amounts of salt just because we have it and it's cheap and we're worried. So let's become aware of how much we really need. So that's what we're doing at Friends of the Muskoka Watershed. We're trying to increase the awareness of the issue, working on continuous monitoring of some places, identifying the main salt sources and the main periods of interest for Muskoka Bay and Jevons Lake, and supporting groups that wish to tackle the issue. And we've built this model to predict chloride from conductivity. We are going to develop a specific water quality guideline for Muskoka, which reflects our low calcium waters and the toxicity of chloride here. We'd like to put some monitors into Muskoka Bay to try to understand what's going on with depth there without having to go out and stand on the ice to do that all the time. Working on a citizen science program, working with Muskoka Steamship and Discovery Center to try to get a salt display into there and some live monitoring of what's going on in the bay. Monitoring the Jevons Lake, which is our worst lake for chloride inputs inflow, and working with other associations. So that's all I have to say, and I thank you for your attention, and we will take some interest now. There are some questions.
Thank you,
Thanks, Amanda.
Neil. That was amazing. So much great information and knowledge in there. We do have a couple questions that have come through. So Stephen had asked about alternatives to salt application, which you sort of, I think, covered towards the end of the presentation, for different alternatives and reusing salt and things like that. But if you have any more specific questions,
Yeah.
Stephen,
Well, I think
yeah,
the ideal there is for something that we can use as freely and liberally and cheaply as road salt. The trouble is most alternatives, we probably find out in 10 years that there's a problem with that too. Just because it's not road salt doesn't mean it's safe. One example is people have talked about beet juice as an alternative. Well, beet juice has an oxygen demand. So when it runs off in a stream, the beet juice has to break down. That takes oxygen out of the water to do that. There are some reasonable ones, like what we call pickled sand is a 3% road salt to sand mixture, which the sand tends to stick in the road after the ice has melted it, after the salt has melted it, and provides longer lasting protection. There are other alternatives that I know that there's a grant in from Queen's University, an application to look at the toxicity of alternatives, but I'm not sure if that grant has been funded. But I really think we should focus on reducing it and just applying it where it's needed as the easy first step.
Great. Another question from Becca, is there an amount of salt that would not negatively impact water quality? Is there a safe level of input that's been found?
Well, the safe level of input would depend on the water body. Of course, you could add a lot more to a big lake than a small lake, but it's the concentration that matters. And that's why we're saying that the federal government says 120 should be safe across, as a general rule, across Canada. We think that the value is much closer to 10 or 20 parts per million in Muskoka because our waters are so soft and have low calcium. So the safe level is really dependent on the calcium content of the water that's there. And then the dose to achieve that concentration would be specific to that water body.
Okay. Another question from Becca was, do vegetated buffers along shorelines help reduce salt entering lakes? So do plants uptake the salt at all, or do they just stop it from moving?
Plants will take up salt a bit, but when the plants die, that salt will simply leach out again. Too much salt is toxic to plants, and I think plants would take up some chloride. There are salt tolerant species out there, but I wouldn't call them anywhere near 100% effective.
Not the best solution. Lisa just asked if we can get the link to the webinar, and we will send that out later today once we get it all up on YouTube. One question I have was, are there any citizen science opportunities right now that you could share that anyone that's attending the webinar might be interested in joining, and how they might be able to do that?
Well, I'll say with confidence that winter is almost over, so maybe we're a bit late for this year, but certainly contact the Friends of the Muskoka Watershed, phone our number and ask for Spencer, and we can certainly hook you up. We can provide you with the equipment. And we probably have a few key areas that we would like to have citizens monitor for us.
Fantastic. I see Laura put her hand up, so go ahead, Laura.
Thanks, Neil. I wondered if, like, it's more of a comment, I guess, than a question. I was a member with Landscape Ontario, and they do a lot with snow removal, like Snowposium, I think is like often hosted in Muskoka. And I just wondered, like, I feel like a lot of the salt is obviously coming from like the users, like the snowplow guys, and they're putting like the landscapers, especially in Muskoka, kind of do dual trade. If you reach out to them through that, like through Landscape Ontario, if you've tried to get them on board.
Thank you. Not personally, but I know that they are very much engaged for the reasons that you mentioned, Laura, is that their insurance rates are skyrocketing because of fears of liability for reducing
Yeah.
road salt. They actually sponsored a Queen's Park Day where I believe Premier Ford came and certainly some of the representatives, and they are lobbying the government to try to limit the liability, maybe following the New Hampshire model, where if you are certified that you can achieve your end with a much lower dose and you follow those certification rules, then you are immune from prosecution if somebody hurts themselves. I'll add that our former MPP Norm Miller, there used to be an unlimited time period where you could sue somebody for slipping on ice of years. He got that reduced, I think, to several months, where if you have to decide if you're injured immediately, well, when you could prove it, if you're going to sue somebody for it. So he did successfully limit the liability period on that. And I know the government is working towards ways to both maintain safety and remove the liability risk for the landscape applicators. So yes, they are involved.
Okay, perfect. Thank you.
Awesome. I think we've got a few more comments in here. So Linda also mentioned the benthic water testing with Muskoka district biologists, I think as a citizen science opportunity that people can get involved with at the district level. And then Carol said 3 Mile Lake has had blue-green algae blooms for at least the past 15 years, and their chloride levels range from 9 to 12 ppm. So seemingly salt may not be a big issue for us. What do you recommend for us to come up with a plan of action since we believe our stakes are high for our lake health?
Whoa, there's a lot involved in that.
Yeah.
First of all, one of the things that Norman Yan and I are considering is that even if you don't kill the zooplankton in the lake, the zooplankton, the water fleas are very important filter feeders. They maintain low algae levels by filtering the water and eating the algae in them. So if they're not eating well, or if they're suffering somehow, you would expect there might be more algae present in the lake. And so that's one of the things that we're working on. There is evidence from about 40 worldwide studies that chlorophyll levels or algae levels do increase as chloride levels increase. And the mechanism there may be zooplankton grazing. I don't know if that's a linkage to blooms, but it could be a linkage to algae in general. The whole 3 Mile Lake study is a whole different seminar on what we have to be measuring to do something about 3 Mile Lake.
Yes, thank you very much. You are a rock star and make all this science easy for us citizen scientists to try to understand. We know it's such a complex issue and multifaceted, and just trying to come up with a solution, but it's so difficult. So thank you very much for everything you do.
Thank you very much, Carol.
Mm-hmm. I think that's all the questions we have so far, and we are at 11 o'clock. So I'll say thank you, Neil, for a wonderful presentation. I'm sure Neil will be happy to answer any other questions you guys have via email if you have any other questions that come up. But thank you, everyone, for participating today, and thank you, Neil.
Okay, thank you, Amanda, and thanks for listening, everybody. Great to see you.
Mm-hmm. Yes, take care,
Goodbye.
everyone.
And get out there and shovel your snow. Don't put any
Yes.
salt down.
Yep, we're getting some snow today.
Don't do salt.
No salt.
Okay, bye-bye.
Take care, everyone.